Yes, welcome all. Welcome back to our TCS seminar at Jagiellonian. It's almost the end of the winter semester here. Most of us are counting days to the semester break. But anyway, today our speaker is Tuukka Korhonen from University of Bergen. So Tuukka is a PhD student under the supervision of Fyodor Fomin. And from what I can tell, lots of his work concerns FPT or approximation algorithm for various graph, width parameters of graph classes, yes. Most prominently, the treewidth, which is also the topic of his lecture today. So Tuukka, thank you for joining us, and we're ready whenever you're ready.
Yeah, thanks for the introduction, and thanks for inviting me to speak here, and thanks also Michal Filipczuk for recommending me to speak here. So yeah, I will tell about an improved parameterized algorithm for treewidth. That's joint work with Daniel Lokshtanov. So this is something quite new work. So so it's an archive. We submit to archive in like November. Yeah. So let's start. I'll start by just defining treewidth, but I know, like, I looked at the past presentation in this seminar, and there was a lot of presentations about treewidth. So I think most of you know these definitions, but let me just say them to be on the same page. So we have some example. We have a graph G, and here's an example of tree decomposition of the graph G. So it's a tree where for every node of the tree we have some back that is like a subset of vertices. Okay, and then to be a tree decomposition, it has to satisfy some properties. So every vertex of the graph G should be in some back of the tree decomposition, and every edge should be in some back of the tree decomposition. So for example, here we have this edge between A and B. So we must have some back that contains both A and B. So this means both endpoints of the edge should be in the back. And then we have that the backs containing vertex should form a connected subtree. So let's say vertex I, it's containing this, and this back. So it forms a connected subtree. And yeah, then the width of tree decomposition is the maximum back size -1. So here we have actually all back size here are 3, which is not you can have backs of different sizes, but yeah. So the width of this decomposition it's 2, and tree width of graph is the minimum width of tree decomposition, and the tree width of this graph turns out to be 2. Well, because it's not a forest, and it has a tree decomposition of width 2, so it must have a 2. Okay, and what else to say here? Yeah, and this definition or the definition of treewidth, not this exact definition, it's been given multiple times independently by different people, and maybe this is actually a bit motivating for the exact computing of treewidth, that actually this exact definition, not like approximately equivalent, but really the exact same parameter has been defined independently by multiple people. So even the exact value of treewidth, it should be something fundamental. So like Petra Priossi defined it in the 70s, and Hallin in 70s, and of course Robertson Seymour gave this definition and the word treewidth in the graph minus series. Okay, and yeah, let's go directly to computing treewidth. So okay, I don't know if I should motivate too much about why we are interested in computing treewidth. Well, it has a lot of graph theory properties, and it's also like it's very useful in algorithms. A lot of times if your algorithm is a tree decomposition of small width, then you can do good things about it, good things with it. You can do like FPT algorithms parameterized by treewidth, where they like you have some NP-hard problem like independent set, and so you want to say that okay, the exponential dependency is only in treewidth and not in the graph size. And this is not only for just doing algorithms parameters per tree width just for the sake of tree width, but it also happens as a subroutine in multiple places. And also it turns out that often tree width turns out to be like the parameter that makes the most sense. Like for many problems, it's like the most general parameter that you can use to do something. So I hope you believe computing tree width and the associated optimal tree composition is a quite well motivated problem. And so computing a tree width of a given graph, it's in 80s, Arbor, Cornell, and Praskorowski proved that it's NP complete. And they also gave an algorithm that works in time n to the k plus 2. So where n is the number of vertices of the input graph and k is the tree width of the input graph. So this is something called XP algorithm in contrast to FPT algorithm. So this is like polynomial time for each fixed value of k, but here, unlike in many algorithms that use tree width, it's like f of k times poly n. Here, the degree of the polynomial depends on the tree width, and this is not what we want. So we want an algorithm of this form, where time complexity is like f of k. So we have some multiplicative factor depends on the tree width k of the graph, and then we have some fixed polynomial like here n square. So this f of k times n squared time algorithm for computing tree width exactly and data composition was given by Robertson Seymour in their graph minus series. But this algorithm is non-constructive in many senses. Like it depends on the forbidden minors, and I think this algorithm actually doesn't construct the decomposition, but you can use some self-reaction to construct it. And this f of k is like horrible in this algorithm. More constructive algorithm, more practical algorithm was given by Portlander and Klocks and Lagergren and Arbor independently. So there's like two separate papers in ICALP 91 where they got the time complexity to be like instead of huge f of k with some forbidden minors, it's only 2 to the O of k cube times n log square n. And it's like what's going on in this algorithm is like first it uses some 8 approximation for tree width given by Lagergren in 1990 with this kind of time complexity, and then it uses dynamic programming on top of the tree decomposition to compute tree width in exactly in this. To compute, like you have some approximate tree decomposition, and then you use dynamic programming to compute the optimal tree decomposition. And this dynamic programming is this 2 to the O of k cube times n. So this is actually linear, and the whole scheme was improved to be like 2 to the O of k cube times linear n. So linear n is like best possible dependency on n by Portlander in 93. So by Portlander's result, so this algorithm is still used the same dynamic programming, this Portlander Klocks dynamic programming, compute tree width, but there is some nice self-reduction trick inside to make it work in linear time. And and so we have for any fixed k, we have a linear time algorithm for computing tree width given by Portlander 30 years ago. But the dependency is like exponential in k cube, while in many algorithms that use tree width, this dependency on tree width is actually a lot better, like 2 to the O of k. So it's like in the exponent you have linear function on k instead of like k cube. And this was in FPT algorithms. This was for a long time open problem. If this dependency on k in this algorithm for treewidth, if it can be improved from exponential in k cube. So this was asked already by Daniel and fellows like in '99, like before anybody else really cared about the dependency on k. They asked this, can you improve it in the treewidth? Then also a bunch of other people have mentioned this problem in subsequent papers about computing treewidth. And yeah, and the result that I'll talk today is that with Daniel, we resolve this open problem if this dependency on k in FPT algorithms for treewidth, if it can be improved. So we give an algorithm the dependency on k is exponential in k square instead of k cube, but the dependency on n is actually quite a lot of worse. But anyway, this result it breaks this like over 30-year-old barrier on this exponential in k cube versus exponential in k square. And yeah, and yeah, even if you don't care too much about like if it's k square or if it's k cube, I think this result should be interesting in that we use like completely different techniques than this like dynamic programming algorithm of Portlander. Like we don't do any dynamic programming on tree decomposition. Instead we do like basically a branching algorithm and then some other things on top of it. And like our algorithm is polynomial space for like even for large k, it runs in polynomial space, unlike dynamic programming on treewidth. Yeah, so that's the main result we'll talk about. Then we have in this book we have another result about approximating treewidth. So let's see some history about approximating treewidth. So it's like there is some polynomial time square root of log k approximation of Bergen given 2008. And then it's like there is this SSE conjecture, which is, I heard, a quite controversial conjecture that assuming this conjecture, it's and be hard to construct approximate treewidth, but it's not clear if this conjecture makes sense or not. Yeah, but so this is like the status of purely polynomial time approximation of treewidth. Okay, maybe I should say what it means to approximate treewidth. So usually here it means that you want to output, you really want to output a decomposition whose width is like some factor worse than the treewidth of the graph. Yeah, but for FP algorithms, of course, there's like this classical Robertson-Seymour algorithm for graph minors, which already gives 4 approximation of treewidth in quite efficient time, like single exponential k. So this is already like better than our new exact algorithm times square. And this is like some people improved, like Matosik and Thomas, like again and Reed, improve this dependency on n in the start of the 90s. And then this was an important result, but under triangle Regge in Loxton and Pilitsuk gave 5 approximation in time that's like linear in n times like single exponential, like exponential in linear function of k in 2016. And I improved it like 2 years ago. I improved this approximation to 2 approximation, and actually like these techniques from my 2 approximation, they are like in like this paper of me and Daniel, it develops these techniques even further. So this can be seen as like continuation of this work in some sense. And yeah, and in this paper with Daniel, what we do, we give like 1 plus epsilon approximation. So it's like the setting here is that the epsilon is really, it's a parameter that you can give as an input to the algorithm. so it's like, you can think of it like epsilon is like 0.1, for example, that runs in time like k to the O of k divided by epsilon times n to the 4. So again, this dependency on n is really bad here compared to prior work, but what's novel about this another result is that we can go below 2 approximation in time like k to the O of k. So before that, like anything below 2 approximation, it was like as bad as the exact algorithms, but now we have some trade-off below this 2 approximation. And yeah, and one more thing you can ask is like what is the relation of this approximation scheme and this exact algorithm of this previous slide. So basically, let's try if I can do the annotation. If you say that let's say epsilon is equal to 1 over k plus 1 here, then this algorithm, it becomes an exact algorithm, and its running time is like what is it? It's like k to the O of k square. I'm quite bad at writing with this mouse, but and so this is like what comes from this approximation scheme, and this exact thing is really, it's an optimization of this approximation scheme in the limit. So it just optimizes this k from the bottom. You can think like this is like k square log k, so it optimizes log away from the exponent, the exact result. So it's like this approximation algorithm is actually a bit simpler than the exact result that I mentioned, and the exact result is like further just optimizing what's going on. Okay. Yeah, so that's basically the statements and some history of the results. Are there any questions at this point? No? Yeah, so I'll continue to talk something about what's actually happening in this algorithms. Yeah. So, okay, so the outline of the talk and the algorithm is that there is basically 2 parts in this result. So our first part that is really so the first part is like more conceptual, and the second part is like more technical maybe. And the first part is that we show that to compute treewidth, or to compute like optimal tree composition, it's sufficient to solve a problem that we call subset treewidth. So this subset treewidth is a new problem that we invent for the sake of this paper and for the sake of computing treewidth. So we show that computing treewidth reduces to solving this subset treewidth problem, and maybe somewhat miraculously, like actually solving this subset treewidth problem, we can do it a bit faster than we could do treewidth before. So so the second part is actually then solving this subset treewidth problem. And it's also like what's going on here for the approximation is that there's like some version of the subset treewidth that will be used for the approximation, and there's like yeah, but this will be like main thing of the first part will be really like how to improve a tree composition. It only thing you need to do is to solve this subset treewidth problem, and this is like something that can be useful even in further work, like this bottleneck of to the O of k square. It doesn't come from this first part, it comes from the second part. So this first part is really something that can be reused, and I hope it finds some more applications than just this paper. And it also, yeah, didn't look too much into it, but it maybe also gives some like refinement of the notion of lean decompositions for the people, yeah, where if you're interested in lean tree decompositions, then this might give something new related to them. But yeah, let's go into it. So yeah, first part, how to improve a tree decomposition. So the setting is we have a treating function t, and let's say we have a back w. Let's say w is the largest back, and now what we want to do, we want to improve this treating position. So we have some non-optimal treating position, and we want to do some operation that improves the decomposition. And the goal here, in how we say treating position is improved, is that okay, this w, it's the largest back, and we want to decrease the number of backs of the largest size, so number of backs of the size of size w, and not increase the width of the decomposition. Or we want to conclude that the treating position we have is already like optimal, or in the case of approximation, it's already approximately optimal. Okay, and you can see that if you repeat this kind of loop, that you improve, and then conclude, once you cannot improve anymore, you conclude as optimal, then you will end up with an optimal decomposition. And basically, here's there are multiple. So you can we can assume that we start with a treating position of width like constant factor away from optimal by like either doing self-reduction of Portlander or just applying some approximation first. So let's assume we start with decomposition of width like 2 times the tree width, and then we just need to do like tree width times n iterations of this, because it's like first you have like at most n backs of the largest size, so you reduce the number of backs of largest size like n times, and then what must happen is that you get rid of the all largest backs, and which must decrease. So repeating this kind of loop is what we're going to do. This is what we mean by improving a treating position. Okay. And we really will focus on this back large back w, and assume, and let's always draw this decomposition so that w is in the root. Here we assume we start with some constant factor, approximately optimal decomposition. Okay. So now, okay, let's say we have this decomposition t that we want to improve, and let's say w is the largest back. So w is like the set of vertices of the back. And now what we want to find to improve it, we want to find a set of vertices x that is a superset of this w, and we want to find a treating position of a graph called torso of x. I will soon explain this definition of torso for those of you who don't remember it. And we want to find we want that this decomposition of torso x has width at most size of w minus 2. So what's okay? So this is convoluted way, because of this -1 in the definition, convoluted way of saying that this treating position of torso x should have strictly smaller width than the treating position t. So we want to find the decomposition with strictly smaller width than the width of t. So this will be like because the width of t is like size of w minus 1, so we want to have this width at most size of w minus 2. Okay. And this problem we will call the subset tree problem. So we're given the largest back, and we want to find this x and treating position of torso x. Okay, and and so what's the definition of the torso? Let's look at the example. So let's have this graph G like this big ghost. And let's have the x is some set of vertices inside of it. And how this torso x is defined is that we look at the connected components of G minus x. So like this set and this set and this set and this set. And we make the neighborhoods of these components into a cliques. Okay. So these are like the arms of the ghost. And then we cut off the arms of the ghost. So we delete from this graph everything that's not in x. So this is like this is a subgraph induced by x plus all the edges that can be formed by like doing a path that goes completely outside of x. So these green things in this picture, this represent this like these cliques that are neighborhoods of these components. Okay. Yeah. So we want to have this torso axis to have a small treewidth. Okay, and let's do some observations of what's going on. So the first thing that we should notice with the subset treewidth is that if this decomposition T that we originally have, if this is not an optimal tree decomposition, then this kind of set X always exists. So then there always is a solution for subset treewidth, but it's just taking X to be like all of the vertices of the graph and taking the optimal tree decomposition of the graph. So it's like if X is like all the vertices, then this torso axis is just the same as G. Okay. But the point here is that now why this problem is somehow useful for us is that we have a freedom to choose X that is perhaps not everything in not all vertices of the graph. So for example, here is some example. So if I have like a graph like this, and this W is like these vertices here inside, and in this picture, let's say, yeah, I forget, maybe I said this picture should look like the optimal tree decomposition. So now, for example, what I can do to select smaller X, I could, for example, prune from this decomposition these things that are like leaves that do not contain any of these like vertices from this W. Like you can think of them like terminal vertices. You can prune leaves as long as they do not contain any of these terminal vertices. So you can really make this X smaller. So you can really think about this as like selecting this X to cover this set W, so that you can somehow, this is okay, what to say, some subset of like good tree decomposition. And yeah, and why you can do this pruning is why this is still tree decomposition torso axis. Like okay, you prune something here, and okay, it gives some connectivity outside of X, but now this connectivity, it's like this single back blocks everything. So here is maybe we have a new click, but it doesn't matter because the click is completely contained inside this back. So that's why this is like this torso is usually very useful thing when working with tree decompositions. Yeah. And another formulation of this subset treewidth is that we want to find a tree decomposition of the graph so that okay, and now this is like tree decomposition of the whole graph, so that the internal backs have size like at most W-1. Okay, so the width of the internal backs is like W-2, and they cover this W. But these leaf backs can be arbitrarily large. So you can think of this also as like putting just this connected components that are hanging into just some large leaf backs. Okay, so this is like what we call big leaf formulation of this substrate, which is sometimes it's actually very useful for getting some intuition of this. Like it depends on the setting, like which formulation of this is like more useful for intuition. Yeah. So is there any questions about these definitions? No. Okay. Yeah. Let's.
One question. In that big leaf formulation, shouldn't the W vertices be necessarily within internal backs?
Yeah. So whose internal backs have size and take cover.
Okay. Yeah. Sorry. Yeah.
So yeah. So the W should be containing like the internal backs. Yeah. That's. Yeah. So let's continue to actually. Okay. So now let's say how we actually improve the tree decomposition given a solution to this subset tree. So now let's have this. We have this decomposition T and this large back W. Now we say we actually have this solution to this subset tree. So we have this set X that is a superset of W, and we have this tree decomposition TX torso axis of like better width than T. And how we improve it? Well, so here's the old T. So okay, yeah, let's first look how this set X looks on top of this tree T. So let's say this green area is like this X. So it maybe looks like something like this. And then we have like three components like C1, three components of like G minus X, like C1 here, C2 here, C3 here. And yeah, then what's the construction of how do we get a better decomposition by using this TX? Well, of course, like the natural thing is to start with this TX. So we know this TX is better than this T. So we start by just looking at this TX here, okay? And now what's going on is that because it's a decomposition of torso axis, now for each of these components, we have some back that contains the neighborhood of that component into X. Okay, so we have some back that contains neighborhood of C1, we have some back neighborhood C2, neighborhood C3. Now, what we want to do, we want to basically put attach to these backs containing neighborhoods these decompositions of three decompositions of like this C1 and like yeah, and neighborhood. Like this is this here, it will be like three decomposition of C1. So this is like three decomposition of yeah, closed neighborhood of C1. So it's like C1 union the neighborhood of C1. This is decomposition of closed neighborhood of C2 and closed neighborhood of C3. And how do we construct these decompositions? Is basically I have here some notation that's probably not extremely clear. So how we construct this decomposition is we take this part of the T that touches this C1. So we just copy this decomposition, okay? And then we set like, let's say the new back is like back B prime. So here we have like back B, and we want to say back B prime here. Well, we take first, we take B intersection of the components. So when we're constructing decomposition of like C1, we just take the intersection with the closed neighborhood of C1. Okay, and now for sure, this is like doing this for all backs here. It gives you decomposition of like closed neighborhood of C1. Okay, and it's not worse at all. But what we have to do, this is not all of it. We have to attach this decomposition into this T of X. So so what's going on is that the interface here will be the neighborhood of C1. So we must have that in this decomposition, this n of C1, it should live also in the root. So we want to make sure that this copied decomposition, it contains this n of C1 in the root, so that we are able to attach it to this TX. Okay, so and how do we do it? We just do like really the naive thing. So let's say we have this this copy here, and like say this is the root, and we have some, let's say we have some vertex. Let's say this is like, here's a vertex V that's in the neighborhood of C1. It lives in some subtree of this decomposition, but it doesn't go all the way up the root. Okay, so then we just make this vertex V to go up the root. So in this P prime, to construct this P prime, we insert to like all of these P primes in the like path from the subtree where this V lives to the root. We insert this V. So this P prime is constructed as this intersection, but then taking like I use this quite weird notation of, I use like B to the n of C, n of C1 to denote So this is like this thing is like a subset of n of C1 that we have to include this back to make this this n of C1 to live also in the root. So we have to add some vertices to make it go all the way up to the root. And yeah, so this is the definition of the construction. Is there some question about this definition? So this is just the definition. This next slide I will explain like how to make sure that this is actually an improvement. But is there a question about this definition? No? Okay. Good. Let's clear these drawings and let's go to the next slide. Okay, so we have this construction. We have this T, and we have this X, and we have this Tx of this torso X, and we want to use this to improve the, and we do this construction, and we want to say that this actually improved decomposition. Okay, and the first thing to do is to even make sure that this new decomposition that it doesn't increase the width. So like a priori with this definition, like with this is let's say B prime is like would this be in the section and of C1 union. With this definition, it's like not clear at all that adding this stuff here doesn't actually increase the width of the decomposition. Okay. So this is like the first thing we want to make sure.
Can I interrupt you for a moment? Just maybe I will get a better understanding. So, the central part of your figure is Tx. This is the tree decomposition. This is the improved tree decomposition that someone gives you of this superset X.
Yeah, it's someone gives me this, and I know this is already like very good. Yeah.
Okay, and then the things that you attach are like I could look at it as they are like a copies of the T, but just projected to respective components and just fixed that this neighborhood is on the interface. So on the, but does it mean that that you consider rooted tree decomposition? Where is the root of the T?
Yeah, so yeah, that's a good point. So so in this, it's useful to think. It's very important actually to think about this as a rooted. So yeah, and it's actually a very important aspect of why this algorithm even works, is to say that actually I say that this W is the root back.
Oh, it's the root back.
Yeah, W that we want to improve is the root back. Yeah, and this is actually, it will be very important in like the proof. Yeah.
Okay, thanks.
Yeah, and this is then, yeah, you can, yeah, it's then it's like just restriction to this closed neighborhood and then just forcing this neighborhood to be in the root. Yeah, just like you said. Yeah. Yeah, thanks. Thanks. That's a good clarifying question. Yeah. Yes, so we want that this thing doesn't grow for some reason too much. And yeah, and here let's see, I want to maybe do some sketch of how the proof will work. So I don't know how much. So you said it's like 60 to 90 minutes. I have time.
Yeah, just relax and tell us the proof. Come on.
Yeah, I don't know completely, but I can give like a nice part of the proof. Yeah, so we want to make so this will not hold a priori this feature that this is not larger than or back, but we need some extra property. So we need that this T of X, this decomposition is pre-processed so that it's every bag is linked in the W. And by linked, what I mean, do I have I don't have definition by linked? I just mean that there's like the flow from this bag back to W has size at least this back. So we don't have any separator between this back and W of size smaller than this back by Menger's theorem. Okay, and why this will work? I'll draw some picture. So let's say that this B is here. Okay, let's say this, and let's say this C1 is a component looks something like, and here's the root W. So root W is like here, and C1 is like this component. Okay, maybe I shouldn't draw it like that. And then I have like the neighborhood of C1 here. Okay, and this is like the picture of the decomposition as like W is up, it's root, and this B is somewhere like in the middle. And now, what is the new B prime, how it's constructed, is I take the intersection of B with this close neighborhood of C1, like this. And then I add what is in this neighborhood of C1 and is below this B. So I add this part of this neighborhood that is below, okay? And what is not taken into this new B is like this part here on the right, okay? So we add this and kick out this, okay? And now, if you think, if we have that this some back contains this N of C1, and this back is linked into W, means we have this disjoint paths. We have this flow from this to W, and now we know that everything that we add, this flow makes sure that we kick out something for everything we add, and yeah, and this is really like the central proof, and the central proof technique here is to have always some flow in the decomposition, and to say that because we have this flow, we know that we add this, and these things kick out these other guys.
Okay, but why the linkage has to go through the right side of the back? Why the path on the left side?
So here on the left side we have component C1.
Yes.
And this flow, what is it? It's from neighborhood of C1 to the W, and W is a subset of X. So this W is contained completely outside of C1. And therefore it doesn't make any sense to like go from this neighborhood back here, and then you need to go back again.
Because the right side is outside the component. Is some
yeah,
other
the right
component.
side doesn't. The right side. Yeah, it's like the left side is the component C1, and the right side is, and we know this W to which this is linked is on the left side.
So any path that would go through the no, it doesn't make sense to go through the left side, you say. So you can control these linkages, or you know that these linkages have to go through the right?
Yeah, I mean, if I have a flow, I know I have a flow whose size that like uses all vertices of this neighborhood. And if it would go right here and come back, then a single path of this flow would use two vertices.
Yes, okay, I see, okay.
Yeah.
Thanks.
Yeah. So, yeah, I don't know if I have enough time to tell any other proofs like in this detail, but this is like somehow the most important picture here, and also like similar thing is in the two approximation algorithm, similar type of argument, and this is like from a paper of like Bellenbaum-Diestel on lean decompositions. They have this similar argument. Okay, maybe I clear this drawing now. That's the point is that if you have some flow in the decomposition, then it must intersect these backs that it goes through. And and this argument, okay, it works if we have this preprocess so that every bag is linked in the W, And now it's like through this pre-processing, it's like what we do, we have some back that's not linked in the W. And now we have some separator here. So, okay, what I want to say. Okay, so this is like, and now I want to say that, yeah, I have some separator here. And now I want to say that if this happens, then I can make this X smaller. Then I can actually change this T of X so that it includes this small separator instead of this back behind this small separator. And again, use this kind of path going inside the tree decomposition type arguments to argue that, okay, we get a good decomposition and show that, okay, this X actually goes smaller when we do this kind of exchange here. Yeah, I don't know how formally I want to go through this, or do you have some?
Start with X being what, the full set of vertices? What is your initial X?
The initial X is something that I've given. But the important thing is the initial X is like, at this point, I'm still in the phase that I have some magic guy. Just give me this X and the decomposition of torso X. And this is my initial thing. And then I use this argument to say, okay, if something is not linked, then I look at the separator and make it, and make a new X and make a new decomposition of torso X. And then I argue that, okay, this new thing is also has width small enough, and what's important is that, like, okay, this B here, it's like larger than this separator between this B and W. So this size of this vertex at X, when I do this kind of exchange, it will go smaller. So I cannot do this like infinitely. Okay. This argument. Okay. Yeah. So, and here, like, in like the true approximation, I had this kind of argument that was somehow like implicit. I actually didn't have to do this exchange. I just have to use it in a proof. But here in this paper, we have to do this explicit exchange, and this is like the part that actually gives this like under the 4 path complexity, like just pre-processing this TX decomposition around. Yeah. Yeah, so this is, I don't know, yeah, I hope you get some flavor of the proof ideas used here. So this is like the main proof for this, like the first part of the algorithm. And yeah. And yeah, and yeah, one more point on this slide, that actually we need bit stronger condition than linkedness for actually improving. So this linkedness is needed for just guaranteeing that the width doesn't go worse, but to actually guarantee that it improves. Like what can happen is like, okay, I have some back, but then I get like multiple components that intersect its back. I get multiple copies of this back. Maybe this is like one of the largest backs, and I get like multiple largest backs. And I want to make sure that like only one of these copies is like largest. So in the end, what will be the argument will be like this back W, like all copies of this back W will be like inside this green area. So that's fine. We lose one largest back, and for all other backs, large backs here, there will be like at most one copy here that has the same size, and other copies have smaller size. So then we get strictly like less backs of this large size. Yeah. Okay, let's go forward. So yeah, then yeah, let's just recap what's going on. So here is like the definition of substitutory problem. So we have this graph. Now we have like more formal definition. Maybe we have this graph G, we have integer K, and we have the set W of vertices of size K plus 2. And now we want to output this set X, that's a superset of W, and a tree decomposition torso X of width at most K. Or we want to say that, okay, we cannot find this set, so the tree width of G is larger than K. So we can, like, here are like two different ways you can phrase this. Like, you can say that, okay, we cannot find this set, or you can just say that, okay, tree width of G is larger than K, but maybe we could even find this. But anyway, that's not very important nuance. But anyway, it's like you can put this in a theorem saying that if there is like f of k times Boolean algorithm for subset tree width, then there is f of k times Boolean algorithm for tree width with the same function f. So yeah, where the k is like this parameter of this size w that we want to cover, and like the target width. Okay, and yeah, this formulation is like if and only if, actually, because if it's like if you have an algorithm for tree width, you can use it to solve a subset tree width in like a trivial way. And yeah, and what happens in our algorithm is like for subset tree width we give 2 to the O of k square times n square algorithm, and this then gives, by going through this old pre-processing stuff and whatever, this gives this to the O of k square times 4 algorithm for tree width. Yeah. And for approximation algorithms, it's like you can do the same thing, but now instead you're allowed to say I don't find any solution a bit earlier. And for this, what we do, we go through a problem called partitioned subset tree width. So it's the same as subset tree width, except this set W that we want to cover is partitioned into T clicks. So in the T sets W1 through WT that are clicks in the graph G. And now I have like two parameters. I have parameter like K, this target width, and this T, how many clicks this is partitioned. And okay, I have an ugly theorem statement, but what this says is that to get like 1 plus epsilon approximation, it's sufficient to look for partition subset tree width where T is like 1 over epsilon. So it's like if you want like 1.1 approximation for tree width, then it's sufficient to look for partition subset tree width where your set W is partitioned into like I don't know, 20 clicks. Yeah, so it's like formal statement. If there's like f of k t times Boolean algorithm for partition subset tree width, then there is like f of k. So k goes to k, and like 1 over epsilon goes to t time like 1 plus epsilon approximation algorithm for tree width with the same function f. And yeah, this is how our approximation algorithm happens. And here is like the connection on how you use how you get this partition thing is not that hard. So the main point here is that, okay, if we want approximation, we can afford to increase the tree width a bit by making some clicks in the graph. And basically you can prove that if you are willing to increase the tree width by like epsilon k, then you can partition this to like yeah, 10 and you have some set of size like about k, then you can partition it like k over epsilon sets and make each of them into clicks. And this is not too hard to prove. It's like some standard like the DFS like argument on tree decomposition, and this we use for this approximation scheme. So it's like this approximation algorithm, in the end it will be like exact algorithm for this partition subset tree width. And this exact algorithm is also like it's nicer to see as an algorithm for partition subset tree width, where it's just like you start with the clicks of size 1. Like this partition is like just these are like single vertex clicks. Yeah, so now I'll say something about this subset tree problem, how to actually solve this subset tree problem. And yeah, and the goal will be to actually sketch an algorithm for this partitions of treewidth with time complexity like k to the of kt, where t is like the number of these clicks, k is the target treewidth, and this is like yeah, this is also an algorithm for subset treewidth by starting with the clicks of size 1, and it's like the reason why I do partition subset treewidth here is not because I want to go for the full generality, but it's because this this is what naturally happens in the algorithm. Like naturally in the algorithm, we will start with these single vertex like terminals and make them into terminals that are a bit larger clicks. And yeah, so this is like the setting. So this could be like a recursive algorithm that calls itself. So for each recursion, the input is like this graph G and this T terminal clicks W1 through WT, and integer K will be the target width. And here this doesn't need to be partition. Like in the statement of partitions of the treewidth, I can say that okay, this is partition, but here these clicks can overlap. And this picture you can imagine is like this is the graph, and you have these 3 clicks W1, W2, W3 here. Now we want to find this X that covers all of this and a tree composition of this torso axis of width most K. And yeah, it's a bit, I don't know if this is a really good way to start explain this algorithm, because now I assume I have already like made these clicks into a bit larger. So these clicks have now some number of vertices somehow. So I'm in some recursion in the algorithm. And what's important thing is we have a reduction rule that we can use. So if you have 2 clicks here, we have like W1 and let's say W3, and we have some separator S between them. And if this is a minimum size separator, and if this is a non-trivial, what I mean by non-trivial is like non-trivial minimum size separator is like a minimum size separator that's not equal to W1 or W3. So it must be different. So I cannot say that, okay, the separator is just same as W1. I cannot say it's just same as W3, but it has to be something different, but this has to be minimum size. And I say that always when we have this minimum size separator that is non-trivial, we can do like a greedy reduction rule when computing subset treewidth. So what the reduction rule will be, okay, we have this non-trivial separator, we can make it into a terminal click. So we can add a new terminal click into our list of clicks. Now it's like a click separator that must be in this X. So it's quite natural that what we can do now, we can cut the graph from here and solve these 2 sides independently of each other. And yeah, and here again, like this will be this is like very crucial step for the algorithm to do this kind of reduction rule. And again, like the proof why this is correct is like, okay, for sure, if you have treating like these torso decompositions for something like this and something like this, then for sure you can glue them together on these clicks. So this must be like, okay, yeah, I make this S, also I make it a click, and I make it a terminal click. For sure I can glue the solutions together like this. But why then I have to prove that this is safe to do, that actually if I can solve this problem, then I can solve both of these problems. And for this, the argument is again some, like I look at the paths going inside the decomposition, like this is minimum size separator. So I have some flow here through here, so that like this includes all vertices of S. And now I can say that to construct like the decomposition, let's say we want to imagine that we have a solution of this, and we want to construct the decomposition of the right side. What we want to do, we want to somehow accommodate this new click S. And how we do it, we just we have this flow, and we just put, like we have this vertex S here, and we have some flow that goes through this, and this flow is all of these vertices I have thrown away. There are different components, so I can use these places where this path was in the previous decomposition to construct the new decomposition, and these paths, they all go to this W1. So and this is a click, so they all go into single click, so they go into single back. And now this back where W1 was, I can use to accommodate this new click as here in the graph, by just doing this kind of what we call like a pulling argument along this flow path here. Okay, and this type of arguments is really like everywhere in this paper, just like this kind of thing that you look for some, you have some flow, and then you use it to say that, okay, I can use this flow to argue that to make some other tree decomposition from some other tree decomposition. Yeah, let's clear this this drawing, and yeah. So this is the reduction rule, and I don't have many slides left. I hope I can be ready in 10 minutes. Less than 10 minutes. So now what happens is like we have this, when we cannot anymore do this reduction rule, when we cannot find this non-trivial separator, we say that, okay, now this terminal clicks, we say, is strongly linked into each other. Like there's no any like non-trivial minimums or separator between them. And okay. Now what we want to do to make progress, we want to increase the size of some terminal click. So the point is like we have T terminal clicks, and this operation doesn't increase them, and we want to just increase the sizes, and like if we manage to increase all of the sizes to like K, then it's like then we are done. Then we cannot increase the size anymore, and we clearly find the decomposition by the reduction rule. So we want to increase the sizes of these terminal clicks, or like it's like here it's not formally good to say that we want to increase the size, but we want to increase some invariant that depends on like how much flow we have from these clicks to another clicks, and which is actually really convoluted definition. But the addition, we want to increase the size, or like how well they're connected to the other terminal clicks. Okay, and for this, we now have some branching. Now comes the actual branching in the algorithm. So what happens is that we can prove that there must exist some solution, some like X and the decomposition of X, so that this W2 click is in a leaf back. And not only is it's in a leaf back, but also it's like we have a leaf back that contains this, so it contains maybe something else, but also this W2, and then it has a parent. I mean, going to this from this leaf to this parent, we forget one vertex, and this forget vertex is one vertex of W2. Okay, this you can prove by just like some greedy arguments. Now, to increase the size of this W2, what we want to do, we want to guess this this back that it's contained in. So it's contained in some back, and it's not all of the back, because otherwise, like we could do some other greedy things. So we want to guess these vertices and add to here. Guess some vertices in the same back and add here. So we want, yeah, guess the rest of this back basically. And to do this, we use like we look in the graph where we delete this back. So we guess this forget vertex. Okay, we guess this. So this is one guess in the branching, and then we look at the graph where we delete everything from this click except this forget vertex. And now what we want to do, we want to take a separator from this forget vertex towards the other terminal clicks. And this is like something called, and we want to take an important separator in this graph. So this is important separator is like a notion, it was invented by Daniel Marks in like 2006, but it's basically the point is that this is like a separator that's optimal in a sense that it's so, you know, it's like if you have just like min cut, then you have like unique rightmost min cut. But you can generalize this if you have like separator of size k, then you have like bounded number of separators of size k that are like pushed most to the right. And this is like important separator. So we want to guess like an important separator that dominates this parent back, that's more closer to this other terminal clicks than this parent back was. And now we can prove that, okay, we can add this, we can say that, okay, this important separator, we can as well say that this is the back this was in. So we can add this important separator in this click W2. And we can basically, and now we can forget everything that's happening in the like subtree below this leaf back, basically. So we can just throw them away outside of X. We don't need to care about what happens in this part of the decomposition. And yeah, this is how we managed to increase the size of this leaf. Okay. And yeah, so what's happening is that this branching, we guess this forget vertex, we guess this important separator, and we increase the size of this click by like at least 1. So we do, and we have the sizes of the terminal clicks is like at most k times t. So we are like branching depth at most kt. So we have like so this gives, because there's like 2 to the k important separators, this gives like 2 to the k, the kt, which is not good enough. But to optimize this to the k to the O of kt, we need some like important separator hitting set lemma that we can guess like only one vertex of the important separator a bit more efficiently than guessing like all of the important separator. And this will give like this type of time complexity. Okay. Yeah, so that's basically what I want to say about this algorithm, what I have time to say about this algorithm. And so let's go to conclusion. I want to mention some obvious open questions like, okay, can we improve this? Is there like 2 to the O of k to the 1.999? That's probably an algorithm for treewidth. And why I want to mention this obvious question is that Daniel believes strongly that yes, this should be we should be able to improve this, but I'm more skeptical. I don't know if we can improve it or not, but yeah, we will see. And another important problem around like this framework is that if we have this t, which is like the number of clicks to which this W is partitioned in the subset problem, if this t is like constant, then do we have like 2 to the O of k as probably an algorithm for partitions of treewidth? And this is like yeah, this is important because this would give like approximation scheme with this type of time complexity, which would be like really nice, I think. Right now we have like k to the O of k, but 2 to the O of k would be much nicer, I think. Or not much nicer, but reasonable amount nicer. And yeah, obvious open question, how much can we improve the polynomial factor? And yeah, another question related to exact computing treewidth is that like for a lot of problems in parameterized algorithms, we have lower bounds assuming exponential time hypothesis, and for a lot of problems we have really like tight upper and lower bounds. But for treewidth, it's like the situation is much more open than for most of the problems, which is I think amazing because we have some fundamental problem for which there is like a lot to work on. So so currently it's like the best lower bound is like I think 2 to the square root k. I'm not 100% sure, but I think like 10p hardness proof gives like 2 to the square root of k lower bound, and we have upper bound is like 2 to the k square. So we have a huge gap, and well, one thing direction of proving lower bounds is to prove like even 2 to the like 2 to the k like or like 2 to the omega of k lower bound for treewidth parameters by k. Yeah, so so that's all. Thank you.